All right, welcome back, everybody. In this video, we are going to introduce the so-called method of partial fractions, that is, integration using partial fractions. And the idea here is that we want to be able to integrate these so-called rational functions, right? So these are functions that we sort of see up here. They kind of look like this. They are rational in the sense that they are a polynomial function divided by another polynomial function, right? And remember, polynomial functions are expressions of the form, usually, some coefficient out front, x to the n, plus some other coefficient, x to the n minus 1. I should really, give these names. If we want to make it look super formal, we can write something like this, plus dot, 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 plus a sub 2 x squared plus a sub 1 times x plus a sub 0. So anything that has this general form is a polynomial, right? Those are all constant numbers times x raised to an integer power. So for example, 3x squared minus 1 is a polynomial. X cubed minus x is also a polynomial. And so this expression, one polynomial divided by another, is what we might call a rational function. Also, something like this, just the constant number 1 is technically a polynomial, right? It just so happens that all of these other terms disappear. And so that's just a constant polynomial 1. So all of these examples up top here are rational functions. And so the idea behind integrating rational functions is as follows. If we happen to know the integral, so let's actually move off to the side here. If we happen to know what our integral is, we can just integrate it straight up. And there are some explicit examples of this. The rational function 1 over x, we know how to integrate that. That is just going to be ln of x. And more broadly, the integral of 1 over x to the n, where n is something other than 1. This is just going to be, well, this is just the same thing as the integral of x to the negative n. And so that's going to be x to the negative n plus 1 divided by negative n plus 1. And I should, of course, throw on some plus c's in all of these. So there are some rational functions we already know how to integrate. Here's another one, the integral of 1 over x squared plus 1. Right? We saw this last time. This is just the inverse tangent or the arctangent function. So we got a couple examples here, but more general rational functions will be harder to compute. For example, this one down here. So the antiderivative, we're asked to find an antiderivative of x minus 7 over x plus 1 times x minus 3. And so the goal, or not the goal, the trick we can use, right? The sort of clever trick we can use is realize that we can actually rewrite this expression right here. And in fact, it will equal this expression down here. So let's actually see this in action. We start by showing it in the opposite order. So we're asked in problem A to rewrite 2 over x plus 1 minus 1 over x minus 3. So these are two rational expressions by themselves, but we want to rewrite it by finding a common denominator, right? And we've all done this at some point. Even if you're a little rusty, I'm confident you've done it at some point in your career. To get the common denominator here, we're going to multiply the top and bottom of this term by x minus 3. So we're going to get that. Minus, and then for the other term, we have this 1 over x minus 3. We'll multiply both the top and bottom of that by x plus 1. Right? And so when the dust settles, the first term, we've got 2 times x minus 3. That second term, we get minus 1 times x plus 1. And now we have this common denominator, so we can move that subtraction into the numerator, because everything is over this common denominator of x plus 1 times x minus 3. And notice when I distribute the top, we get 2x minus 6 minus x minus 1. So 2x minus x, that just gives us a single x. And then the negative 6 minus 1, we get a minus 7. So let's close that parenthesis over there. So the thing we can realize, right, is that this expression, let me grab a new color, this expression here, which was this expression here, can really also be written in this form as two sort of simpler rational expressions, two simpler fractions being added, or in this case, being subtracted from each other. And this is going to be sort of our idea behind the method of partial fractions. We can identify a more complicated rational expression like the one up here by identifying that it can be rewritten or is equivalent to several simpler fractions, what we call partial fractions, down here. And the reason why we might want to do this is because these simpler expressions are actually a lot easier to integrate. So notice in this case, when we rewrite this, we have that this integral, well, from our work above, that's just going to be equal to 2 over x plus 1 minus 1 over x minus 3, right? And because integration splits across addition and subtraction, right? It's linear across addition and subtraction. I can actually calculate the one integral, throw a tiny dx on there, minus the second integral, and I'll throw a tiny dx over there as well. And each of these, because it has a constant in the numerator and a single copy of x in the denominator, right, and like an x plus 1 or an x minus 3, I can solve each of these using substitution. So for the one on the left, I can say let u equal x plus 1. Notice du in this case will just equal dx. And so this integral becomes, let me scroll down just a little bit, give ourselves more room. This integral here becomes the integral of 2 over u du, which, again, the 2 will stay there, and then the 1 over u, that becomes an ln of u. So this whole thing becomes an 2 ln of x plus 1. And similarly, right, if we cut over to this one, the negative 1 over x minus 3, well, there's that negative sign, right? And we can, again, do a u substitution. The details will be exactly the same. Let u equal x minus 3, du equals dx in this case. And so this whole thing becomes negative the integral of 1 over u du, so that becomes negative ln of u, so negative ln, negative ln of x minus 3. And that will give us the answer to the entire problem. We'll take these two things, we'll recombine them, and so our antiderivative that we were searching for is nothing more than 2 ln of x plus 1 minus ln of x minus 3 plus c. Right, and there you have it. So taking this complicated rational expression, recognizing that it can be split into two simpler fractions, and then integrating each of those simpler fractions separately. Now, the hard part, of course, is going to be in the act of splitting. Here, I gave you, right, this is going to be up here, circle that right there. I gave you what this split into, but of course, in general, you won't have that. And so going forward, we'll take a look at how we can determine what the correct splitting will be, and we will do that in class. So this is the idea behind partial fractions. It should be a lot of fun. Can't wait to talk to you about it. I will see you next time.